Okay, let us continue from where we left off in the previous part of this lecture. So we were discussing how to find out the vertical deflection at this point. Now the next question is, how are you going to find out the horizontal deflection at the same point? How are you going to find out the horizontal deflection at that point? What do we do? Take a take a force in this, take a fictitious force in the horizontal direction. Okay, as I said, always use your brain adequately. Don't go for too much imagination at this stage. That stage will come later. Okay, so here we do not have a horizontal force, so we bring in a horizontal force. So now for the horizontal deflection, we have to write del u del q, but with the understanding that ultimately this q has to be set equal to 0. Okay, now see, you have to draw this diagram again. I have the luxury of reutilizing the figures from before, but you have to draw this diagram again. So this picture that we had drawn earlier will remain the same, but additionally now we have a q in the horizontal direction. This q is present. So now our m has to be adjusted in response to this additional q. So let us write that down. M, what will be the contribution to the bending moment due to q? First of all, you tell me what is the moment arm associated with the q for finding out the m at this location. This is the moment arm, and what is that? R minus r cos theta minus pi by 2. Okay, so and the sense is again in the clockwise direction. So this is q r minus r cos this thing remains exactly the same, at least the form. But now we have to do a del m del q, right? We have to do a del m del q, and we have to understand that this entire thing is evaluated at q equal to 0. Okay? Now you see, very quickly the algebra kind of becomes a little bit more involved, but it is still simple. It is long, but it is still simple. Okay, I will not do all those things. Okay, I have many other things to discuss. Many other things to discuss. So, um, I will not do this. So just leave it out. Let us look at another variety of that, another variation of that problem. You finish up, at least if you can find out this expression of moment, half the job is done. However, I will also give you a word of warning. See here, I have left it here. I know all of you can do the integration. You have done much more difficult integrations before coming to IIT. Okay. Of course, some coaching institutes give the funda that in IIT JEE, especially in advanced, I think from integration there is not much marks. So there is not much return of investment for you to learn integration. So maybe drop it. Those are the kinds of advice we are given. But I hope at least if you have gone to school, wait. So at least you have gone to school, you have learned integration. Yes.
So this we are calculating the horizontal displacement.
We are calculating the deflection at the location where the P is applied, but in the horizontal direction.
So then that will take the moment corresponding to both the.
Yes, that is always true. Okay. Earlier also, when we were doing this problem, um, when we were doing this problem, and we asked what is the deflection at this point, then also you have to start from the left end. Whatever the algebra tells you later, that's a different matter. If some contribution is 0, let it be 0. But the entire contribution due to P, due to Q, everything has to be taken. So until the stage where you are setting the Q equal to 0, you have to respect all the forces in finding out the expression of the bending moment. Yes.
And so how will the answer of QH be coming differently than
Which one?
answer delta H will be different from delta.
Very good question. So what he's asking is that if we proceed exactly like this and we are setting Q equal to 0, how is the answer of delta V and delta H going to be different? It is going to be different because of this part. It is del M del Q. Earlier it was del M del P. So there it was just sine theta minus pi by 2, which will be r sine theta. This will be coming out. Here this time this one will be coming out. So the terms will be different. Yes. Yes. Very, you have done the calculation. Okay, very good. So if you have done the calculation and your answer is coming out as delta H as something negative, it basically means that this delta H is opposite in direction to the applied direction of the fictitious force. And does it not make sense? Because you see, no, I'll tell you, don't worry. So see what is happening here. You are pushing down this P. So if you think that this is like a very, very flexible member, then after deflection, so initially it was like this. When you are pressing down really hard on it, then this one will become like this. Okay, so this point will come a little bit to this side, not that side. I mean, my drawing is not very good, but it will come this side. My drawing actually, there is a problem with my drawing because the way that I have drawn it, this entire thing I have kept it rigid, but this is not going to be like that also. Because you see, when this is done like this, what happens is, this is actually, so suppose this was like this. Okay, suppose it was like this. Then what would happen is, it would become something like this. Okay, so there is a flattening also. Okay, now this end is open, because of which it slightly deflects to the left. Or there is an algebra mistake in your answer. Positive. Okay. Okay. But no, but the thing is, I mean, his question is generic enough. It is absolutely possible that sometimes your answer may come out to be negative. The interpretation would be that maybe there is an algebra mistake in your thing, but the interpretation would be that it would be opposite to the applied load Q. Okay, so nothing to worry.
So, but you, in the last diagram, you made a curvature, so you were told that that would be repeated.
Which one?
So, when you told that in curve wheels, the curvature won't be changed much. So, you meant the shape only, right?
No. So this was an extremely exaggerated diagram. If you have a flexibility like this, then it won't be. So I didn't want to go into all of these things. So what I just drew, if it is indeed deflecting like that in such a huge fashion, it is no longer under the purview of small deformation. And if small deformation is not applicable, then Castiglione's theorem is also not applicable. Okay. All right. So let us look at another variation of this problem. Let us erase all of these things. Suppose now you please draw it in a fresh place, okay? In your copy, please don't keep on drawing on the same place. Please draw it in a fresh place. Please draw this diagram again. And then now the question is that what is the here at this point what is the vertical deflection, what is the horizontal deflection? This is a very, very important question. What will you do now? At the location where the deflections are desired, do you have any point forces? This is the first question which you ask yourself. Whenever you encounter a question from here, you first ask yourself this question. At the location where the deflection is desired and in the direction in which the deflection is desired, do you have point forces available? You don't, which means that you have to introduce fictitious forces. Okay, almost algorithmic. All right, so we have to do one by one. First of all, for the vertical deflection. For the vertical deflection, what will you do? Yes.
Introduce a fictitious force at an angle theta. So that what can be.
I mean, if you want to torture yourself, you can do that.
Both answers at the same time.
I mean, you can do that. You can do that, but then you ultimately have to take the components of that. What's the point? Okay. So Q. Now you have to be careful with taking the moment. Earlier, we were very comfortable because from 0 to pi by 2 there was no moment contribution, but this time there will be. Okay, in fact you have to find out the moment in a piecewise fashion. From 0 to pi by 2 there will be one value. Any problem?
So with your method, you will even take it to equal to 0. So ultimately that will be maximum.
No, but you have to do a del m del q, na?
That number is there. And
Yes.
obviously there is a p value, the p moment associated with p.
No. So you have to do this m by ei. To do by this m by ei, but this del m del q. So unless you have a proper expression of m involving the q, you will not be able to find out the correct coefficient here. Okay. So see, you have to actually go through the algebra, right? So otherwise these kinds of mistakes will happen. All right. So as I said, we'll proceed it like good boys and girls. Okay. Let us not jump ahead of ourselves. So we'll find out the m in a piecewise fashion. Okay. So take the cut here. Take the cut here. Isolate the free body. Draw the free body diagram. Okay. Here, this is our theta. This is directly our theta. Okay. So very bad drawing, but okay. Now you tell me what is this m? What is the m? Exactly. Exactly. Very good. So this diagram is a little bit misleading. I will draw it with a higher. Maybe this is a little bit better. Okay. So you see the moment arm here is this much. This is the moment arm. And this much is r minus r cos theta. Okay, so and please also note that now the sense of the moment due to this q is opposite to m. So this thing is true for 0 less than theta less than pi by 2. Okay, next when you take this cut, okay, when you take this cut, then the diagram is like this. This entire thing is the theta. What is the m? First of all, you tell me the contribution from P. Again, the moment arm is this much. Okay, the moment arm is this much. How much is that much? Okay. And what is the contribution from Q? Yes? What is the contribution from Q? You check one thing. Whatever that contribution that you had written earlier, is that correct? That is still correct actually, because the sign will take care of itself. Okay, so that is the, I mean, at least one good thing about trigonometry. So you can actually directly write this thing, q into r 1 minus cos theta. Okay, if you wish, you can divide it from 0 to pi by 2 and then take this angle, then do all these things. Ultimately it will come back to that only. Okay, so this is our expression of m. As I keep telling time and again, this is the challenging bit. Okay, for these curve beam problems, finding out the m is the challenging bit. If you find out, so spend some time, slow down a little bit and find this out correctly. Now we have to just proceed as before. I have already written it here, but now I have to change the expressions. Let us not forget that we have to set q equal to 0. Now, in all these expressions, you have to be careful in which integration you are doing it. When you are from 0 to pi by 2, you have this thing. So it will be r into 1 minus cos theta. Is that going to change in the pi by 2 to pi? It is exactly the same thing. Okay. However, that m expression is different. Okay, that m expression is different. Furthermore, you note that in this 0 to pi by 2, acha, you do it on your, I should not spoon feed everything. I have many other things to discuss actually. That's why I'm stopping. All right. Next, what was left? The horizontal thing. Okay, the horizontal thing. But before that, I mean, we can keep on doing like this. I want to give a slightly different variety of these problems. See, on this thing, I'm doing at this place, at that place, various kinds of deflections. But suppose you have a slightly different kind of a curve beam, which is like this. Uh, okay, suppose this is our curve beam. Entire circle. Okay. Now, if it is an entire circle, everyone listen carefully. Please stop writing. Please stop writing. Listen carefully. Now, the load here could be like this or tensile also. It could be either way, either tensile or compressive. Now, this thing, you may wonder, I mean, am I just playing around here? Not like that, okay? This is actually the basis of a device which is referred to as the proving ring. It is there in your lab. When you do it in your 6th semester, it will be there. Okay, proving ring experiment. And that is actually used as a device to measure force. Measure deflection first and then force. And it is very, very sophisticated. Very sophisticated. In fact, it is so very sophisticated and so very useful that it is actually used in spacecrafts. There is, you can actually search for it, like proving ring in a spacecraft, and not like modern spacecraft. It has been used for quite some time. So, and we have a proving ring in our department, so we'll see that. Now the thing is, one very good thing about it is nice and symmetric. But doing it using the energy methods is not that straightforward. We'll not do this problem. We'll do an easier version of this problem, but I'll tell you the trick, what is done. And this trick is so very universal that it is not just limited to energy methods. Later on, whenever you do these kinds of circular problems anywhere, suppose you want to do a finite element method simulation or some kind of analytical solution, if you encounter this kind of a circle thing, immediately your mind should go that, okay, it is symmetric. How can I reduce my calculations? Now, how can you reduce your calculations? So there is a fourfold symmetry here. Fourfold symmetry means if you draw a horizontal thing, it is symmetric above and below. If you draw a vertical axis, it is symmetric like this. If you take the advantage of this thing, then what is actually happening is that you need not do the entire problem. Okay, you need not do the entire problem. What you will do is, you will only do this part of the problem. Okay, this part of the problem. So you will isolate it like this. Okay, this quarter. Like this is a this is not my trick. Okay, this is a very standard trick in all of solid mechanics. So whenever you have this kind of a thing, just isolate out one quarter. Then the question becomes, like, what will you use at this end and this end? Because in reality there are materials here, there is material here. So the idea here is that, see, if you squish it down like this, do you think there is going to be any deflection at this in the vertical direction? In the vertical direction there is no this thing. And here, do you think there is going to be any horizontal deflection? No, there is only going to be vertical deflection. So one idea is that you use something like this. Okay, one idea is this. But it can even be further simplified. So we'll not talk about this thing. What we'll do is, we'll take the simpler version of this problem.
the symmetry we are taking will depend on forces also.
Yes, of course. Forces, but here it is symmetric, right? It is symmetric. Okay. The simpler version of this problem is that you take a slight slit here. Okay. You just shave off like a fraction of a millimeter here. If you do that, there'll be a small gap here. For all intents and purposes, they are touching. Okay, they are touching. Now, I mean, if you just put this compressive thing, then nothing much is going to happen. Here you are going to get deflections, but here nothing is going to happen. But slightly challenging than that will be, suppose we do this. Okay, suppose we take a force here, or equivalently we take a force here. Then how much is the gap going to be? Okay, that is an important thing to do. Now, why I'm saying that this is simpler is that let's consider this thing only. Okay, let's consider this thing, this simpler problem. Now, does this problem have a symmetry about this horizontal axis? Everyone, if I draw an horizontal axis, does it have this up and down symmetry? Yes. Does it have symmetry about this? No. Okay, because of the presence of this slit, there is no longer a symmetry like this. Okay, this left right symmetry is gone. So you cannot take a quarter. What will you take? Semicircle. Okay, you are going to take a semicircle. So that is literally what we are going to do in order to reduce our computation. You will take an axis like this through the slit, of course, through the slit, and you are just going to take this semicircle. Now, whether there is a tensile load or compressive load, you are all good. Okay, and please note that suppose I take this compressive thing
So now there will be a deflection at the right corner. Now,
here, right? Yes.
then the slit approximation is
So you are probably thinking that steel will overlap steel.
sitting.
Okay, so let us not take compressive since you are unhappy with that. Let us open it up. Okay, fine. No material overlap is there. But the question is what boundary condition we are going to take over here. So for this particular problem, it is enough for us to take like this. Okay, because whatever horizontal deflection may be present here in this horizontal direction, whatever this thing deflects with respect to this, even if you fix it up, this thing will be found out. Yes.
So just to confirm the original problem, there is no split that we have taken only for our.
No. This is a different problem.
Okay,
This is no longer the proving ring. In proving ring, if you have slit, then the thing is damaged. This is not proving ring. Yes. There you have to do it. That's a more difficult problem. It's quite long actually. I'm not doing it. That takes about 40 minutes, 45 minutes. But see, why I am doing this is that all the previous examples that I have been doing, it ultimately boils down to that. Is it not? All the previous examples that I did, it is ultimately boiling down to that. So if someone says that what is the deflection over here, you find out. Okay, we have already done it. What is the horizontal deflection? You find out. If someone asks what is this vertical deflection over here, you find out. Horizontal deflection also you can find out. No problem. Okay. All right. I want to have another variation on this. Um, Suppose I have a curved beam which is like this. This is another semicircle, okay? This is not looking like this. Okay. So everyone please look here. Almost the same kind of previous situation, but now there is a twist. Both the ends are fixed. Now you tell me, this is statically determinate or indeterminate? This is indeterminate. Okay. Now there will be a variation of the question. Question will be, suppose I ask you that what is the, or what are the vertical forces at the two ends? You tell me the answer. P by 2. P by 2. There you don't have to do anything else. Okay. Even first year students can do this. So if this is P and you are asked what is the vertical forces, what are the vertical forces at the two ends? It is P by 2. You don't even have to write the equations, just write P by 2. But suppose someone asks what are the horizontal forces at the two ends? Huh? What? Huh? They are equal. They are equal and opposite. Yes. What is the value? No one knows. So that is what you have to find out.
So we can just remove one and put
You want to remove it.
like you can remove a ground and put a force.
I think you are thinking in the correct direction. Think a little bit more, it will come to you. Uh-huh.
No, no,
So he's thinking in the correct direction. So see, we have already done a similar kind of thing, right? You're just finish your thought. Finish your thought. Very good, very good. Right. So remove this ground. Okay, ground is giving problem. Remove the ground. Okay. So remove the ground. Like make the force appear explicitly. But we know for a fact that the ground actually is there. Okay. So the deflection there will be equal to 0. So the same kind of thing that we had done for our earlier problem, right? So we had done this problem, right? Where we had this distributed load and there was a roller here. What did we do? We removed the roller. We exposed this reaction force, and then we went about finding it out. Exactly the same kind of idea. Okay. So what we'll do is, we'll just so now you have to be a little bit careful. You have to write this P by 2. Okay. This is a common mistake. If you don't write this P by 2, it will be wrong. Okay. This vertical force must be written. And whatever this thing is, some R. No, not R. R will be radius. So some something like H, horizontal force. Okay. Okay. Now you have to proceed just like before. Okay. You just have to take a cut section, expose that cut section, take at theta some moment, find out the moment, do all this. So what will you do? This del H will be equal to 0 to pi m by EI del m. What do I have to write here? Please tell me. Del m del H. Very good. Okay. So now if you just go through your notes, whatever we have discussed today, I have given you the basic ingredients for various types of permutations and combinations that could be possible. Okay, so please go through these examples very nicely. Where? Here? Yeah, there will be moment also.
You cannot comment on it both sides.
There will be a, you are absolutely right. There will be a moment. So I goofed up a little bit in the sense that this original problem had a pinned end. It had a pinned end. Yeah. So, but if I give this problem, then there will be an m naught. You cannot bypass it. You cannot bypass it. But then you tell me, what is the solution now? Huh? Vertical you have already utilized, P by 2. What will you use?
Angle.
Very good, slope. Very good, slope. So this is the thing, you have to put delta H 0, and then you have to take this theta also, 0 to pi m by EI del m naught r d theta. And then again this theta is 0. Okay. So whenever you have a fixed end, that thing will be equal to 0. Very good for pointing it out. The original problem actually was a fixed pinned end. If it is a pinned end, then only one condition will be sufficient. There is no m naught there. Okay, one last problem. अरे you have to be grateful that we are discussing these problems. अचानक से एग्जाम में आ जाएगा तब क्या होगा? Now don't expect कि just because the question paper has been set, I know the question paper, therefore I will do only those problems. Okay, so we have a rod here, a bent rod. Okay, this rod is bent. So this is A, this is B, this is C. This thing that I have drawn here, it depicts the wall to which it is fixed. Okay, so this bent rod is fixed to the wall. Yes. 0 to pi by 2.
As there is a symmetry,
Yes, you can do it. You can do it. But the problem is that once you have removed this ground, no, then it is no longer symmetric. Because now it is a different problem.
but we can remove the other ground as well.
If you remove the other ground, you can try to do it. The issue will be you have to expose this thing, right? At that end, there will be some V and P. There will be some V and M naught also. I have to think about it. I am not very sure. Okay, how will you handle it? Maybe it can be handled, but this one definitely can be handled. Okay. Acha. Now, this is the situation. So it is combined loading combined with energy methods. Okay. ठीक है. See, idea is very simple here, answer is also very simple, but you have to think a little bit here. So everyone just keep your pen down. Think about it, then it's not that difficult. It's almost entertaining. So from A to B, what is happening? Forget about everything else. From A to B, suppose I take a cut section somewhere here, okay, and I expose that, this little bit. This force is here. Okay. So what is this? This is almost like a cantilever beam, almost. Okay. So on this exposed surface, which is this part where I have cut it, you are going to end up with a bending moment like this and a shear force like this. Okay. So from A to B, for the energy methods calculations, you are going to have a contribution to the bending moment from this applied load P, nothing else. Okay. Next, suppose I take a cut over here, somewhere between B and C. Then you tell me what are the different kinds of things that are going to arise at that. Okay. What are the things that are going to arise? First of all, you tell me the most obvious thing which is staring at your face. There is a torsion. Okay, so this kind of an angle thing is here. When you pull on that side, it is going to create a torsion. So over here there is going to be a torsion. How much will be the value of that torsion? I'll give you the lengths. Okay, this length, let's say, is L1, and this length is L2. So this one is how much? P into L1. P into L1. Okay, so this is our torsion. Now, if you look in this horizontal plane, okay, a plane which is horizontal here and parallel to this thing, then on that plane, okay, on that plane, so if you look from the top, what will it look like? So this vertical bit, it is going into the plane, is it not? Is it not? And then this force P is here. This is where your engineering drawing comes into the picture. Okay. So here, do you not think that there is going to be a shear force? There's going to be a shear force. This shear force is in this horizontal plane. So in this horizontal plane, there's going to be a bending moment also. What will be the value of the bending moment? P into x. Very good. P into x. So this much is your x.
Sir, the original force is less it rotated.
Sorry?
Here force is force. Original P, how is it rotated?
So I have tried to do my best for a 3D diagram. So maybe it will be better if I draw an axis something like this.
Shear force is in opposite direction.
No, no, no. So it is something like this, that there is an x here, okay, and there is a y like this. There is a y, and then there is a z. Okay, now it is clear, huh? So the p is along the z. All right. So which plane am I considering here? This is a plane which is parallel to the xz plane, or this is the xz plane. Okay. So there will be a bending moment here also. This bending moment will be equal in magnitude to the px. Okay. It will be equal in magnitude to in fact, it will be equal to px. Okay. So the entire thing boils down to this situation. What are we trying to find out? We are trying to find out the deflection over here, not the vertical or the horizontal deflection. Okay, because in this 3D diagram, we have to be really careful about what we are asking. So we are asking the deflection along the direction of P, the easiest version of the question that is possible. Okay, so we are literally asking the deflection along the direction of P. So delta P, that is going to be equal to A to B, B to C. Okay. Now for A to B, what is there? Only the bending moment is there. So M by EI del M del P D S1. This S1 will go from 0 to L1. I am deliberately choosing a different coordinate system here. Okay. Because my y is placed over here, I don't want to make a mess of it. Okay. So my S1 will go from this 0 to L1. So it is something like this. This is my S1. Next, for 0 to L by L2, what are the contributions? First of all, the torsion. This is the thing. Del del P, this is the entire U. Entire U due to the torsion. Okay. If you are wondering where this has come from, please flip back to your notes where we found out the different expressions for the U, the strain energy corresponding to torsion, to bending, to shear, etc. etc. Next, again 0 to L2. See, this 0 to L2 corresponds to this BC. This 0 to L2 also corresponds to this BC. Okay. However, this contribution is due to the torsion, this contribution will be due to the bending moment. I can write this as dx directly because, but anyway, S2, where my S2 coincides with the x. Now you tell me what is the M. Very quickly. Now you have done sufficient number of problems. Tell me what is the M? Px. If M is Px, then del M del P is what? X. Now this thing, I will make the change over here only. You see, this is del del P of T squared by twice Gj. So this will come out as T by Gj into del T by del P. Okay, what is the T? We have already seen it. T is equal to PL1. Del T del P, how much is it? Del T del 1 is this L1 dx plus M is what? M is again Px. And del M del P is x. Now because I have run out of space, I will skip one step and write down the answer. So P x square. X square means this is L cube by 3. Plus this is PL1 square by Gj coming outside. Inside it will be 0 to L2 dx. So that will be just L2. Plus this is P by EI coming outside, x square, that is L2 cube by 3. So this is P that's it. Okay. And again you see, we have very conveniently neglected the shear. Torsion we are taking because that is not negligible, but shear we are neglecting. Okay. So to recap, energy methods chapter, from my side I have finished. You have lots to learn.